Hi, students. So today we will be discussing chapter 9 in the textbook, and this chapter deals with bivariate analysis. A simpler way to kind of think about this is we're going to be looking at crosstabs. Now, if you don't know what a crosstab is, or if you don't know what bivariate tables are, trust me, when I show you, you're going to be like, "Oh, I've seen that a million times." And we're going to look at how it is that we kind of like analyze crosstabs as the kind of like eyeball test before we start more advanced statistical analysis, for example, like chi-square and the measures of association that we're going to be discussing next week in chapter 10. Okay, so quick introduction. So what is bivariate analysis and what are crosstabs? So bivariate analysis is a statistical method designed to detect and describe the relationship between two variables. And like I said, it's a bit of an eyeball test before we actually start getting into chi-square and the measures of association next week. And cross tabulation, what is that? That's a technique for analyzing the relationship between two variables that are organized in a table. So you have basically like two frequency distributions that are laid on top of each other. So if you're looking at something like race and income or political affiliation and satisfaction with the election outcome, right? So you could kind of take one variable laid across the other, and that would be an example of a crosstab. Now, crosstabs, in a crosstab, the variables are organized on a table to demonstrate the strength of the association and, when appropriate, its direction. Now, you're typically going to be using crosstabs for either nominal or ordinal level data. Okay, now, if you remember from some of the prior lectures, you may remember that I told you that anything that you can do with nominal or ordinal level data, you can also do with interval ratio level data. So it is true that you can create a crosstab with interval ratio level data. Yes, you can. But there's a problem with that. If you do that, basically you're going to have a really, really big crosstab. You're going to have too many categories, and your table and your crosstab is going to be unreadable. So you typically want to do this with either nominal or ordinal level data, nominal and ordinal level data as well. But you wouldn't want to do this with interval ratio level data. Now, when it says when appropriate, its direction, now what it's talking about there is we can do this. We can determine the direction when we have ordinal level data. So for example, with nominal level data, we really can't tell direction because there's no logical order. But when we have ordinal level data, we can actually determine direction in that context. Okay. An example of nominal level data will be like hair color, car brand, dog breed. And an example of ordinal level data would be things like social class, degree level, right? Associates, bachelor's, master's, doctorate, things like that. Military rank. So ordinal level data is, of course, when we have like a logical order to the categories. Nominal level data is when we just have a qualitative difference between the categories, but there's no logical order and there's no logical rank, right? That's the example of nominal level data. Okay, so let's take a look at this. Now, this is an example of a crosstab, okay? Now, the independent variable is always going to be in a column. So the independent variable is going to go up and down, right? Columns go up and down, kind of think like Greek columns, right? Now, the dependent variable is always going to be in the rows. So rows go side to side as if you're rowing a rowboat, right? And of course, it's obvious that race is the independent variable because race, sex, age, those are not typically dependent variables. Like, what would your race depend on? Maybe, I guess, the race of your parents, but, what's the point of even asking that, right? So race is the independent variable that looks at, you know, the dependent variable home ownership. So does race influence home ownership, right? So that's the question that we would be asking here. Now, looking at this data, we just have frequencies in the cells. So this is a cell. A cell is an intersection of a column and a row. So if we're looking at African Americans, how many of them own? There's two. How many of them rent? Four. When you look at white Americans, how many own? Five. How many rent? Four. Now, it's important to understand that when you're looking at crosstabs, you don't just want frequencies, you also want percentages, because percentages allow you to do a comparison amongst the categories of the independent variable. Because if you look at rent, you may say, okay, well, an equal amount of African Americans are renting as white Americans, so it's completely equal. It's not though, right? And the reason why it's not equal is because there's essentially more white Americans in the actual study, right? So proportionally speaking, we look at the percentages, more white Americans own their homes than rent compared to African Americans, right? Now, the way you're typically going to do this when you're looking at a crosstab is you're going to calculate the percentages for the independent variable. Since we know the independent variables are in the columns, we're going to calculate the percentages vertically, okay? So for example, how would you do this? You're going to do two, for African Americans, you would take the cell, African Americans 2, we're going to divide that by 6, right? So 2 divided by 6, and you're essentially going to get 33%. Okay. Now, the percentages should always add up to 100%. So 4 divided by 6, I could put that in a calculator if I want to, but I also know that it's going to just add up to 67%, right? Which would be 100% of the African Americans in that sample, right? Now, if I were to do that for white Americans, okay, I would have to do 5 divided by 9, right? So the cell 5 divided by 9. And I would get, if we're rounding, I would get 56%. And then here, because I know it needs to add up to 100%, I would get 44%. I can also do 4 divided by 9 to check my work to confirm that it is 44%. Okay. So now that we have the percentages, it's easier to do a comparison, right? So we can see that only 33% of African Americans own their home compared to 56% of white Americans, right? 67% of African Americans rent versus 44% of white Americans, right? So even though you have 4 here, 4 here, we don't want to just look at frequency. We also want to look at percentages to do an adequate comparison. Now, the question may arise, well, why don't we calculate the percentages horizontally? Well, you can do that. But if you were to do that, you'd be reversing the analysis, right? You wouldn't be looking at the percentage of African Americans who own or rent or percentage of white Americans who own or rent. You would, if you were to calculate the percentages horizontally for the dependent variable, you'd be looking at the percentage of people who own who just so happen to be African American or just so happen to be white, right? And you would be looking at the percentages of renters who just so happen to be African American or just so happen to be white, right? So what you would be doing is you would be reversing the analysis, and you'd be reversing the analysis in a way that there's not a causal link, and it kind of doesn't really make all that much sense. So we always want to calculate the percentages for the independent variable, not the dependent variable. Although we could calculate it for the dependent variable, not very useful for us. Now, the question I think that a lot of other students have is, well, could I put the percentages or could I put the independent variable in the rows and then calculate the percentages for the rows? Yes, you can. And there are situations in which you would want to do that. But if you're going to do that, you'd want to explain to the reader or whoever it is that's looking at your work why you did that. And like I said, we'll talk about why you might want to do that. And the reason Actually, I'll just explain it right now. Sometimes you have a situation where you have too many categories of the independent variable and it won't actually fit on the page if you do it, you know, vertically, right? So you eventually run out of space. So you might, if you want to have like a lot of categories of the independent variable, you might want to put it vertical, or on in the rows, right? Then calculate the percentages horizontally for the independent variable. But you always want to make sure you're calculating the percentages for the independent variable and not the dependent variable. So the only time you'd want to calculate the percentages for the rows is if your independent variable is in your rows. Okay, so independent variable and dependent variables. What is the independent variable and dependent variable in home ownership by race? We already discussed that. Race is the independent variable, home ownership is the dependent variable. It doesn't make sense the other way around. Okay. And if we were to look at something like what is the independent variable between English proficiency and by nativity, nativity is whether or not you were born in, an English speaking country like America, right? So nativity would be the independent variable, and the dependent variable would be like English proficiency, right? Okay, so now for some variables, whether it is the independent or dependent variable kind of depends on the research question. So for example, you might be looking at like the relationship between poverty and drug use, right? So which one's the independent variable? Which one's the dependent variable? Well, kind of depends on what the researcher is looking at, right? So for example, we could put poverty as the independent variable, right? Where living in poverty perhaps could lead to more drug use, right? So anything to do. Well, I mean, at the very minimum, I feel like at least in the United States, people tend to like sit around drinking a lot when they don't have anything to do or when they have a lot of free time on their hand. But you can also look at how drug use can lead to poverty, right? If you have a drinking problem, if you have a drug problem, right, it could certainly affect your ability to keep a job, and it could certainly affect your ability to be productive in life, right? So, which one's the independent variable? Which one's the dependent variable? Sometimes it's obvious, right? Race, sex, age, those are kind of more fixed. They're never going to be a dependent variable typically. While something like this, poverty versus drug use, you can kind of switch those around. So you just need to make sure that, you know, you're you put the right variable that you're looking at into the independent variable into the columns. Okay, so now how to construct a bivariate table. So a bivariate table displays the distribution of one variable across the categories of another variable. And then what we do is we classify the cases based on their joint scores for the two variables. So as I stated a little bit earlier, you can kind of think about it as a series of frequency distributions joined to make one table. Okay. So for example, if we're looking at race and homeownership, if I were to go to my here, so let's say we're looking at race as one frequency distribution. And I think, I don't know, I think they do. Okay, 6 African Americans and 9 whites. So I'm just gonna put E for black, which is 6, W for white, 9. Okay, so that's like a frequency distribution for the variable race. Now for homeowners, we have own and rent. And then we have another frequency distribution, right? So we have owners and we have renters. So O is for own and R is for rent. And as you can see, there's 7 people who own and 8 responded to rent. And what we're doing with a cross tab is we're basically laying the two tables on top of each other, right? So we're having race goes up, so it's kind of like a frequency distribution going up and down. And then home ownership is going side to side, right? So if you might, and you might notice, I don't know if people noticed yet, the totals for the columns 6 and 9, right, is the same as the frequency distribution that we have for the race frequency distribution, right? So 6 and 9 here for the column total, same as 6 and 9 here, right? And then the row total, right? The row total, 7 and 8 for the variable home ownership, owner, and rent, is the same as the frequency distribution for the home frequency distribution. So basically, you're just kind of taking two frequency distributions, you're laying them on top of each other. And then what this other bullet point says is we must classify the cases based on their joint scores for the two variables. What does that mean? Okay, so what that means is we're taking African Americans. How many African Americans do we have? 6. We have a column total. How many white Americans? 9. We have that, right? How many people own? 7. How many people rent? 8. Okay, now that we have those, then you would look at, okay, how many African Americans are there? 6. How many of them own their house? 2. Okay, how many African Americans are there? 6. How many rent? 4. How many white Americans are there? 9. How many own? 5. How many white Americans are there? 9. How many of them rent? 4. So what you're having is we're classifying them by their joint scores. Now, the intersection of a column and a row is what we refer to as a cell. Pretty easy to count this up. There are 4 cells. 1, 2, 3, 4, 4 cells. These 6, 9, 7, 8 are not cells. They're the column totals and the row totals respectively. Okay, now what should a bivariate table have? Okay, now the first thing is a title that is descriptive. So you should let the reader know what it is that they're looking at. So a title that is descriptive. So for example, homeownership by race. So they should know what they're looking at when they first open up that table. Second thing, it should have 2 dimensions, 1 for each variable. Usually the independent variable is in a column and the dependent variable is in the row, as I stated earlier. Sometimes you can put the independent variable in the rows if you have too many categories and it's not fitting on the page. Okay, but explain to the reader of your study that you did that and explain why you did that and make sure that you calculate the percentages horizontally if you do that. And now the intersection of a row and a column is called a cell, as we discussed earlier. Some other things that a bivariate table should have. Okay, so the column and row totals are the frequency distribution for each variable. I think we talked about that already. So the column total is the frequency distribution for the independent variable, and the row total is the frequency distribution for the dependent variable. And we refer to a table as row by column. So the table on homeownership is a 2x2 table, 2x2. So we have 2 and then 2. Okay. So row by column, right? Now let's just say that I have, instead of black, white, own, rent, let's just say I have black, white, owners, renters, and then I don't know, homeless people, H for homeless. So what type of column would I have? Would I still have a 2x2? No, I would have a 3x2, right? Because we have 3 categories in the row, 2 categories in the column, right? So that'd be a 3x2. So let's just say we have black, white, and then I throw in Latino, and then I have Asian. In this situation, correct, I would have a 3x4. So 3 rows, 4 columns. So I'd have 3x4 table in that situation. Okay. Now, the last couple things that a bivariate table should have, it should have the source of the data, should always clearly be noticed that we are giving credit to the person who came up with the information. Now, if you did the study and this is your data, you don't have to do that. But if let's just say you're pulling it from the General Social Survey, right? Or you say that you're pulling it from some other news organization, some other news source, then you'd want to do note where you got it from. And you'd usually have it somewhere down here with an asterisk that kind of like, US Department of Labor or something like that to denote where you got that information from. Okay, so source of the data should be noted. And then, of course, like I said, need to have column variable, row variable, cell, and marginals is you should know what all these are. I don't know if I pointed this out. Marginal. What is a marginal? It is a total. So a column marginal and a column total are the exact same thing. The textbook refers to both marginal and total. So when they're talking about the column marginal, it means the total. When I talk about the row marginal, it means the row total. Remember that. Memorize that. Okay, now let's talk about calculate percentages. We discussed this a little bit earlier, but I want to make sure that you all understand we calculate the percentages a certain way. Okay. And why do we calculate percentages? It's because it's easier for the reader to see the results and to make comparisons. Like I said, when we looked at that bivariate table earlier, and we looked at the 4 for owners and 4 for renters for blacks and whites, it looked like it's equal. It was equal, but it wasn't equal, right? So when we calculate the percentages, it was much easier to see. It was much easier to see that there were more black renters than white renters, right? More white owners than black owners, right? So when we use percentage, it's easier for the reader to see the results. It's also easier for the reader to make comparisons. And like I said in prior lectures, when you have really, really large, really large frequencies, a lot of times it's difficult for the reader to understand, so percentages are easier for readers. Okay, so to calculate the percentage, you must calculate the percentage within each category of the independent variable. So like I said, since we typically put the independent variable in the columns, an easy rule to remember is to calculate the percentages vertically, calculate the percentages for the columns, okay? And then you're going to interpret the table by comparing the percentage point difference for different categories of the independent variable, right? So let me see if we had this, when we did these percentages, right? Calculate the percentages for the independent variable, the percentages should add up to 100%. And then compare the percentages across the different categories. So how many African Americans own versus white Americans? How many African Americans rent versus white Americans? So that's essentially what that means. Okay, all right, so we interpret the table by comparing the percentage. Interpret the table by comparing the percentage point difference for different categories of the independent variable. Compare the percentages. So the first, this is a repeat. So the first rule means that we have to calculate percentages within the category of the independent variable. And then we, compare those percentages. Now let's look at this. Now, so as I said, sex is one of those that really can't be a dependent variable. So sex is the independent variable in this example. And what we're looking at, we have a title that's descriptive, so it's letting us know what we're looking at, right? The way people voted in the 1992 presidential election by sex. You all, a lot of you weren't even born at this time. So there are 3 major kind of candidates. There's George Bush, the senior, not the one who was the president in 2000 to 2008. Ross Perot, a billionaire, and then Bill Clinton, who actually won that election. So looking at this, we would calculate the percentages for the independent variable, male versus females, and we would see, is there a difference between how males and females voted for in the 1992 presidential election? And there is a difference, right? Males were more likely to have voted for Bush, right? And this is something that you typically do see. Men are more likely to vote Republican. And females were much more likely to have voted for Clinton than males were. And also, males were more likely to have voted for Perot than females. So there does appear to be a relationship between sex and how people voted in 92. Some more thing in 2000. So this was Bush Jr., George W. I believe it was George W. So Al Gore, Buchanan, and then Ralph Nader. Okay, so yeah, the independent variable is sex, right? As you can see, females were much more likely to have voted for Gore. Males were much more likely to have voted for Bush. And there didn't seem to be a huge relationship between sex and who voted for Buchanan and Nader. They didn't get a, or Buchanan certainly didn't seem to have gotten a lot of people, Pat Buchanan's. Okay, so, and we can keep on doing that. In general, females are more likely to vote Democratic and males are more likely to vote Republican, right? Okay, so comparing the percentages. Okay, so the second rule says that after we calculate the percentages for the independent variable, then we compare the percentages across the different categories of the independent variable to see if there's a relationship between the independent variable and the dependent variable. Now, in a 2 by 2 table, there's really only one comparison that needs to be made. But for larger tables, more than one comparison needs to be made. And typically you want to look at the extremes of those tables. And I'll talk about what I mean by comparing the extremes coming up. Okay, so let's take a let's take a look at like some of the properties of a bivariate relationship. So when we're looking at a bivariate relationship, like I said, because it's kind of like an eyeball test, before we start looking at chi-square and the measure of association, the first thing that we're going to look at is, does there appear to be a relationship between two variables? If all the percentages are the same, for the different categories of the independent variable, then there's probably not a relationship there, okay? But if there are differences, percentages that are different, maybe there's something there. So we want to see, is there a difference between the percentages? Now, after we look at the whether or not there is a relationship, then we want to actually look at the strength of the relationship. How strong is the relationship? How big is the percentage gap? Now, it's typically the case that the larger the percentage gap, the stronger the relationship. If we're doing it from an eyeball test, now, like I said, there's an actual mathematical way to determine the strength of the relationship. And we're going to learn about that in chapter 10 with the chi-squares and the measures of association. I don't want to give you an exact number, like, if it's 10% difference or 20% difference, and that is the strength of the association. And the reason why I don't want to tell you that is because, that is heavily influenced by sample size. There's an actual mathematical way to determine the strength of the association. But that's what we're going to be learning next week. I know y'all can't wait to learn it, but you can jump ahead in the textbook if you want to learn about how we determine the strength of the relationship. But right now, just understand that generally the larger the percentage difference, the stronger the association. But that's not set in stone. Okay. And then the third thing that you're going to want to look at is the direction of the relationship. And like I said, you can only determine direction if you are using ordinal level data. If you have nominal level data, there's no clear rank, so there is no real direction involved. You could theoretically, like I said, use interval ratio level data, but if you're using interval ratio level data, you're gonna have a lot of categories. But if you just have like a small amount of categories for your interval ratio level data, then it's possible to create a bivariate table with interval ratio level data. Okay, so determining the existence of a relationship. Does a relationship exist between the two variables? Again, we calculate the percentage of the independent variable, then we compare that percentage difference. Now, let me show you two slides, completely fake data, textbook data, just to illustrate this example. And I want you to look at this and tell me, do you think there's a relationship here? Okay, so independent variable is number of traumas, and support for abortion as the dependent variable, right? Now, looking at this, I think that there's a pretty clear relationship. That is, if you have zero traumas, you typically don't tend to support abortions. One trauma, your support for abortion seems higher. And then two or more, you are really supporting abortion. And it's clearly, it's the opposite, right? On the other side. So if you have no traumas, or if you have zero traumas, your support for abortion is very low, right? If you have one trauma. So basically, when you're looking at this, as you can see, that there's a clear relationship between traumas, the more traumas you experience, and whether or not you support abortion or not, yes or no. Okay. Now here, if we're looking at this, we're doing a comparison of the percentage difference, 46%, 46%, 46%, 54% said no, right? So it doesn't appear that the number of traumas influence whether or not you support abortion or not, right? So if you're seeing all the percentages are pretty much the same, that kind of suggests that there isn't a relationship. When you see the dramatic differences between the percentages, well, that suggests that there is a relationship. Okay, so that's how we determine does a relationship exist, right? When we're doing the eyeball test. Okay. Now, once you have established that there is a relationship, the next step is to see the strength of the relationship. Now, again, the easiest way is to determine the percentage difference across the different categories of the independent variable. Again, the larger the difference across the categories, the stronger the association, that is, the larger the percentage difference. But like I said, we're going to learn about mathematically how to determine the strength in chapter 10. Okay. So in this hypothetical example of no relationship between trauma and attitude toward abortion, there's a 0% difference between the columns, which is the second side that we showed. On the other extreme, if like all the women who suffered one or more trauma were pro-choice and supported abortion, then we would have 100% correlation, 100% be a causal relationship, which is something you never really see with the social science. You never see this perfect relationship like, oh, well, if you had a trauma, well, then you're definitely supporting abortion. If you had no trauma, then you're definitely not supporting abortion. We never see stuff like that. Typically, we never see stuff like that. Okay, so the direction of the relationship, like I said, in order to determine direction, you need, okay, so you need ordinal level data. So when both the independent and dependent variable in the bivariate table are measured at the ordinal level, we can look at the direction of the relationship. Now, there are two types of relationships. There are positive relationships and negative relationships. This textbook uses the term positive and negative. I don't like those terms. Other textbooks use terms such as inverse. Actually, well, they do use inverse, but wrong one. So direct for a positive relationship and inverse for a negative relationship. So what do I mean by that? So let's just say we're looking at the more you eat, the more you weigh. So the independent variable is eat or food consumption, right? And then weight. Okay. So the more you eat, the more you weigh, right? So that's a direct positive relationship, right? But it can also go the other way, right? That is, the less you eat, right, the less you weigh. Now, that is still a positive relationship. It's still a positive direct relationship because the two variables are moving in the same direction, right? So when we talk about a positive relationship, that means that the two variables vary in the same direction. They're going in the same direction. Either they're both going up together or they're both going down together. So positive doesn't mean that it's going up, although when you think about the term positive, you're thinking, oh, well, they're going up. But that's not the way the textbook uses the term positive. It means it as a direct relationship, okay? So when it says, when the independent variable increases, so does the dependent variable, or as the independent variable decreases, so does the dependent variable, okay? Now, a good example would be social class as the independent variable, and then your health, right? So as you can see, as your social class increases, your health outcomes increase as well, right? So high people from the high social class and they have like about 63% rate their health as good versus, people from the lower class, only 25% rated their health as good. Now, going back to that kind of slide a little bit earlier where I said you want to look at the extremes when you have more than a 2 by 2 table. So for example, I wouldn't want to look at like the middle class. I would want to look at the middle class a little bit, but what I would want to focus on are the extremes. So the high class and the low class, right? I would want to look at the poor and the good as opposed to the fair in the middle, right? Because that's where you start to see the more extreme examples of a relationship. People from the high class, 63% of them said they're in good health versus the low class, only 25%. That's a big difference. That's a big gap, right? Now, if we look at people in the lower class, 39% said they're in poor health versus people in the higher class, only 9% said that they're in poor health, right? That's a 30 percentage point difference. That's a big difference, right? Now, again, you still do see that kind of relationship for people in the middle class. There is a difference between high, middle, and low, right? But as you can see, the percentages are not as extreme when we're getting into the fair and the middle, right? So that's why I tell students a better way to kind of like look at cross tabs, especially when there's a lot of categories. This is just a 3 by 3 table, right? You have like a 5 by 5 or a 6 by 6. It's easier to focus on the extreme, like the high and the low and the poor and the good versus the fair and the middle in this example. Okay. So that is an example of a positive relationship, okay, where the two variables are going in the same direction, either going up together or going down together. Now, a negative relationship, in a negative bivariate relationship, the two variables vary in the opposite direction. So as one goes up, the other one goes down, or as one goes down, the other one goes up. Okay. So when one variable increases, the other variable will decrease. So can we think of an example here with a negative relationship? Let's just say the more vegetables. I don't even know if I spelled that right, so I'm just gonna put vegetables. So the more vegetables you eat, perhaps the less you weigh. Right, so that might be a relationship. Or let's just say that a negative relationship. Let's just say the more TV you watch, the worse your grades. And it's important to understand here that correlation does not mean causation. You could watch TV and still get good grades, if you're both watching a lot of TV and also studying. But we all know TV is the idiot box. If you spend too much time on TV, well, it's going to be difficult for you to have time to do other things like read and, do other types of activities that can improve yourself as a person, whether or not that's exercising or relaxing in various ways, getting out, getting fresh air, or like I said, potentially reading and studying. But again, correlation doesn't mean causation, right? I mean, you could just watch TV, a lot of TV, and still have time for other things, depending on how much TV you're watching, right? Okay, so that's an example of a negative relationship. And another example of that would be looking at the relationship between social class and traumas. People from, again, I want to focus on the extreme. People from the highest social class, only 20% of them experience 2 or more trauma versus people from the lower social class, 47% of them experience 2 or more trauma. When you look at, people from the high social class, only 48% of them experience 0 trauma versus people from the lower class, 15% of them, only 15% of them experience 0 trauma throughout their lifetime. So this is not real data, in case you're wondering. It's just textbooks giving this out as an example. But this kind of illustrates this example of a negative. As your social class goes up, the percentage of or the number of traumas you experience throughout your lifetime goes down. And vice versa. As your stress class goes down, the number of traumas you're going to experience throughout your life goes up. All right, so let's talk a little bit about elaboration. So what is elaboration? So elaboration is a process designed to further explore a bivariate relationship. What does that mean? Basically, what we're doing is we're introducing something we refer to as control variables to see if they explain the bivariate relationship a little bit better, right? Or whether I can completely take this relationship away. That's the potential. Okay, now there's three goals of elaboration. The first one is to test for non-spuriousness. Big term, not super complicated. We'll discuss that on the next slide. A second thing that elaboration does is it clarifies the causal sequence by introducing what we refer to as like an intervening variable. So sometimes there's a relationship, not clear how or why they're related, and so we can introduce intervening variable to help explain a little bit better. And the third goal of elaboration is it specifies the different conditions under which the original bivariate relationship might hold or potentially might not hold. Does it make sense? We're going to, well, those 3 points probably don't make sense, but they're going to make sense as we progress. Okay, now the first thing that elaboration does is it allows us to test for non-spuriousness. So this shows us if there's a cause and effect relationship between the independent and dependent variable and a bivariable relationship. It also establishes time order, yada, yada. We also want to know if there's a relationship between the variable that better fits relationship. Okay, so a lot of stuff there. Let's go ahead and like try to make this a little bit simpler. Okay, now in every major American city, we've actually seen this done. It's actually a real relationship. That is, as ice cream consumption increases, we also see a increase in violent crimes. This is a real relationship, in case you're wondering. I'm not making this up. Now you might think to yourself, well, wow, do I need to just completely cut out ice cream out of my diet? Do we need to have a national ban on ice cream? Of course not, right? So this is a real relationship that we see, but this is what we'd refer to as a spurious, right? So spurious. Spurious. I think there might be a U there. Check that. Yeah, there is a U. Spurious relationship. Okay. That is, the two are correlated, but it's not causal, right? Ice cream does not cause an increase in violent crimes, right? And so what elaboration allows us to do is to introduce a third variable that might better explain this relationship, right? Now, to kind of help suggest what might be going on here is we also see the relationship between ice cream. As ice cream consumption increases, we also see an increase in drowning death. What's happening? Is ice cream causing all these horrible things, or people mugging and killing people because, ice cream? Are people drowning because of ice cream? No. The third variable that could actually better explain this is heat. As summer approaches, as it gets hotter, as it gets warmer, people tend to be a lot more irritable, people tend to get out of the house more, so they're walking around, they're in situations, they're out at night more often, so they're in situations in which they're easily agitated and they're easily victims because they're just walking around at night more often, and things are much more likely to happen when heat increases, right? Now, not only does heat cause an increase in violent crime, but it also causes an increase in ice cream consumption, right? So if you introduce this third variable, which is heat and temperature, we see that this relationship goes away, right? That ice cream consumption increases with heat, violent crime increases with heat. So even though there's a correlation, there's not a causal effect. Same thing with drowning, right? As the temperature increases, people are more likely to go to the beach or go out to the pool, and they're more likely to drown, not because ice cream has anything to do with it, but rather because there's just more people out at the beach, there's more people swimming in pools to cool off, and as a result, you're gonna see more people drowning. Okay, so and then the other thing when it says it establishes time order, right? So it's you can say that ice cream and violent crimes are related, but there's no time order here, right? Heat, we can say heat precedes ice cream consumption. As it gets hotter, people are more likely to eat ice cream. As it gets hotter, people are more likely to commit a violent crime, right? We haven't even established here that ice cream precedes violent crime. It's completely possible. Somebody goes out and mugs somebody and like super hot, needs to cool off and goes get ice cream. Or maybe somebody's the victim needs to cool off, goes get ice cream, right? So there's not even like a timer established. Okay, so when we're testing for non-spurious, we want to make sure that we're looking at a direct causal relationship. And it's very difficult to establish like a direct causal relationship because correlation does not mean causation. So you can see that there's a relationship between the two variables, but that does not mean that one variable inherently causes the other. In order to do that, you need to make sure that you control for all other potentially theoretically relevant variables, which is very difficult because it's easy to potentially miss a third relevant variable. Now, and also you need to establish time order. You need to make sure that the independent variable precedes the dependent variable, either rising or decreasing, right? So now a spurious relationship is a relationship in which both the independent variable and dependent variable are influenced by a causally prior control variable. And there is no real causal link between them. So like ice cream and crime, there's no causal link. And they're actually being influenced by a third variable, which is heat, right? And once you introduce this third variable, that relationship is completely explained away. Now, a good example of this as well would be looking at the number of firefighters in a region and the amount of property damage that we see in that region. Now, there is a relationship between the number of firefighters in an area and the amount of property damage caused by fire in that same area. But is it the case that firefighters are destroying property and lighting things on fire for the purpose of justifying their existence? Of course not. We deploy firefighters to fire-prone regions, so there's more firefighters there, right? We've also seen this relationship, um, with doctors in an area and the outbreaks of diseases. Some people say that the more doctors you have, the more likely you are to see crazy outbreaks, right? Again, spurious relationship, right? We deploy doctors and the World Health Organization and various organizations to areas that actually need medical treatment. The doctors are not causing the problems. The doctors are going there to help to alleviate the issue, right? Okay. Okay, so spurious relationship, like I said, example, sites fire causes an increase in the number of firefighters and also an increase in the amount of damage caused by a fire. Okay, now a direct causal relationship would be looking at something like your level of education and your social class, right? That's a direct causal relationship where your education level does impact your social class, and a lot of times impacts your income as well. So, and one of the reasons why this is because your education level is one of the measures that we use to determine your social class. If you took introduction of sociology, you would know that there's typically three measures that we use to determine your social class: education level one, income number two, and job prestige number three. Okay. So, level of education is directly impacting your social class. Okay. Now, the second effect of elaboration is it clarifies the causal sequence. So sometimes we know that these two variables are related, but we don't know how or why. So what you can do is introduce what we refer to as an intervening variable that unlike a spurious relationship where it completely explains the relationship away, this helps to explain the relationship, right? Another thing about a spurious relationship is typically the third variable kind of precedes the other two and impacts them both. With an intervening variable, what essentially happens is that it follows the independent variable, but then precedes the dependent variable. So there's kind of like a third variable that comes and helps explain this relationship better. So that is by introducing what we refer to as an intervening variable. So, for example, let's just say that we're looking at, we can go back to that slide later, but let's just say we're looking at father's education and son's income. Yes, there is a correlation between a father's education and a son's income, which if you look at it on its surface, doesn't completely make sense, right? I can see how a father's education would influence his own income, right? But how does a father's education influence his son's income? That is questionable, right? So we look at an intervening variable. Again, it's a control variable that follows the independent variable, but then precedes the dependent variable, right? So there's this kind of like this third variable that needs to be put in to kind of help us explain that relationship between the two variables. So it basically kind of intervenes and mediates between these two variables. Okay. So, for example, father's education, son's income. Not clear how these two are related. But what we do know is that father's education does influence a son's education, right? It's an unfortunate reality, especially seeing it's how we're at a community college right now. But it's an unfortunate reality that you're more likely to graduate and get a degree if your parents have a college degree. Okay. So a father's education can influence a son's education, right? However, having stated that, which might be a little bit pessimistic, might sound a bit pessimistic, um, today, it's kind of expected that people get bachelor's degrees and college degrees. So people are much more likely to get degrees today than they were, 20 or 30 years ago when your parents' generation were going to school. So yeah, and it's also the case that, the only thing that's going to stop you from getting your degree is yourself. There's so many opportunities, community college. You're here right now. It's free. The only thing that's going to stop you is yourself from getting your education, right? So, but we do know that there is a link between parental education level and child education level. So father's education can influence the son's education, and it makes sense. So it makes sense that a son's education does influence their own income. So this is an example of an intervening variable, right? That helps you better explain that relationship. Hopefully that makes sense to everybody. Okay, now the third goal of elaboration is to specify conditional relationships. So a conditional relationship is a relationship between an independent variable that differs for different conditions of the control variable. Now this is a little difficult for some people to understand, so we're going to walk through this. We're going to walk through it in a way that I like to use, and I like to use sports as an analogy, okay? So what other variables may explain the relationship between father's education and son's income? Well, let's just forget about that for a second. Let's talk about sports. Let's just say that I'm looking at the relationship between field goal percentage, sports, and free throw percentage. That is, typically it's the case is as you're good, a field goal in basketball, we're talking about basketball here, field goal percentage is just whenever you take a shot from any point on a basketball court, except for a free throw, that would be considered a field goal. So a 3-pointer is a field goal, a 2-pointer, layup, a jump shot, a dunk, those are all considered field goals, right? So typically it's the case that the higher your field goal percentage is, the better your free throw percentage is. Because if you're good at just shooting 3-pointers and jump shots and layups, that usually means that you're a pretty good shooter. And then that usually correlates to a free throw, right? Which is when you get fouled, you sometimes get two shots from the free throw where nobody can like block your shot or nobody can play defense against you. Or if you are shooting a 3-pointer or somebody fouls you, then you get three shots, right? So there's usually a direct correlation between field goal percentage and free throw percentage. And now this relationship does hold, right? For the majority of shooters, um, for the majority of shooters, as your field goal percentage increases, so does your free throw percentage. But there is one group of players where this relationship does not hold, where field goal percentage is not tied to free throw percentage. And that condition or that group is actually big men or centers, power forwards. Now, why you might ask? Why it couple different reasons. I don't want to get into too much of like basketball theory and how we train people today versus how we train people back in the days. But short summary, big men, particularly like centers and power forwards, they tend to shoot around the basket, like layups and dunks, right? Well, if you can dunk a ball consistently, it's pretty much the easiest shot to make, right? So if you can dunk the ball and you're doing it consistently, your field goal percentage might be around 75 to 80%, or if you're shooting just like dunks and layups, right? But once you're really, really tall, a lot of times, especially back in the days, they would discourage you from learning how to shoot the 3 pointers. Like, hey, if you're big, just go down there and dunk the ball. If you're Shaquille O'Neal, just dunk the ball. Why worry about shooting a 3-pointer? You're much more effective down low. Okay, so they would never really train big men to learn the proper mechanics of shooting. And so a lot of times they weren't good free throw shooters, right? So there was kind of like kind of like a negative relationship between field goal percentage and free throw percentage, right? But with pretty much everybody else, like a point guard, a shooting guard, or wing player, you were shooting, sometimes you would dunk the ball, but the vast majority of the time you were shooting jump shots or you were shooting from the corner, you were shooting 3-pointer, right? So your mechanics for shooting were good, and that also correlated to the free throw line as well, because the free throw line is not super close to the basket, right? So you have to have a certain level of skill to knock down both field goals, 3-pointers, and free throws, right? So that's why you typically tend to see the positive relationship for point guards, shooting guards, and wing players, and then a negative or inverse relationship for centers and power forwards. Although, like I said, I don't want to get into too much basketball theory. These positions are not as relevant today as they were in the past. Nowadays, you have centers shooting 3-pointers all the time. So that relationship still kind of holds, but not complete. So condition one is like more for like wing players, point guards, and shooting guards. And condition two is more for like big men. And so what elaboration allows us to do is introduce the third variable, which is like kind of the position that you play and how in that situation the relationship holds for condition one, for small men, you might call them, and for condition two, big men, the condition is kind of like the opposite, right? Okay, now one thing about elaboration is it's kind of just a stab in the dark. Typically, the way you introduce control variables, two ways. One, do a literature review to see what other researchers who are looking at the same thing or similar things that you're looking at, what they have to say about using control variables. That's the first thing you're gonna do. The second thing is you're gonna use just what you think of as like theoretically relevant and try to introduce those. But there's always the possibility that you can miss an important variable, that you both missed an important variable, And all the prior researchers have missed an important third variable as well. You're doing an educated guess, you're doing your best. Okay, anyways, so that was the lecture for today. If you have questions, shoot me an email, come to office hours, and I can help you all out. Good luck this week.